Well, thank you all for attending another APEX AU, or as I should say, our new name, Australasian Supply Chain Institute, or ASCII, webinar. This afternoon, we have a fantastic webinar, number 2 in the series, from Sean Gates regarding MEIO. And just a little bit about Sean. He's actually delivered for us previously, and you can jump onto our website and get access to the first webinar that he presented if you missed out on that. Sean is the Managing Director of Lexion Solutions, has extensive experience in inventory management, forecasting, network optimization, modeling, event management, transportation systems, and warehouse management technology. Lexion installs and markets a number of LlamaSoft technologies, including inventory optimization, Cast, Aurora, CastFlow, as well as Supply Chain Guru and their family of products. So, guys, without any further ado, I would like to hand over to Sean. He will take you through MEIO. If you do have any questions whatsoever, please feel free at the end of the webinar to email us at events@asci, that's ASCI, .org.au, and I'll be more than happy to pass them on to Sean. Otherwise, please enjoy the webinar. Over to you, Sean.
Right, sorry for that delay. We're just swapping chairs. Technology is meant to make things easier, but I think at times it makes things more difficult. So anyway, welcome, and thank you very much for your time today. My previous webinar, we really just talked about conceptually what MEIO was, how it would work, etc. And I would encourage you to look at that webinar on the website. Today, we're going to look in a bit more detail, actually, some of the calculations behind multi-echelon inventory optimization. I will pace myself. There's a bit to go through, and there are some concepts we need to deal with, but we'll work through those as we go. There we go. Just getting used to Clint's computer. The motivation for safety stock optimization. Something I guess the audience would be very familiar with. It's our bread and butter. And the safety stock is really there to deal with uncertainties in supply and demand. It's our inability to predict the future sales, and also the lead time variability. So how well our supplier, whether external or internal, is able to meet stated lead times. And I'll just show you on this graph. You can see, the typical sawtooth graph that we have. Our sales over time, you can see that line going down. The line's never completely even. If we have a period of time when we don't sell, it will flatten out. And a period of time when we sell more rapidly, it will actually decline more rapidly. And you can see that there. We typically hit the reorder point. We place the order. Our stock continues to go down during our lead time. And in this case, you can see we've got a stock out. We have a resupply, and the stock goes back up again. So something we're all fairly familiar with. And again, we'll come to that concept as we go through. Safety stock optimization. What questions does it answer? Before I go through a couple of these slides, safety stock, certainly in my 20 years of experience, tends to make up the biggest component of inventory within almost every business I've dealt with. So your cycle stock, where you order and sell, tends to look after itself. Safety stock is really a big lump of stock that often very rarely moves and often is very inappropriately profiled across the network. Demand characteristics, and we'll come to that. We really need to do 2, 3, 4 slides on what that means. Where and at what stage and how much safety stock do we need within the network? Do we keep it at components level or finished good level? And when or what level to replenish inventory, so reorder points. And that's, again, part of the safety stock calculation. What problems do we solve? Strategic impact of network changes to inventory policies. What happens if we add another DC, or we take a DC away, or we have more branches, or we added a new supplier, so we've now got common suppliers. How does that affect the inventory? What stocking strategies should be deployed for which products? The make to order versus make to stock. And we've got, I think, a great little example where we'll go through those options and see what the effect is on the safety stock through a very simple network. Postponement strategies, and determining which products need a pull versus push strategy. So where do we keep stock in the network? Do we keep it further downstream, or do we upstream towards the customer? And what inventory deployment strategies do I use for which SKUs, centralized versus decentralized? It's the age-old question. Anybody that's been in this field will have had this dilemma. Where do we keep our stock? Do we stick it all into the DC in Melbourne, or do we push it out to the branches where we can provide a better service? But then ultimately you end up with more stock. Monthly inventory planning uses safety stock recommendations from SSO. SSO is Safety Stock Optimisation. It's a little 3-letter acronym. Everyone's got to have one. How do I reduce days of supply while still meeting service levels? The big question. How do I reduce stock and still have adequate service levels? Understanding inventory requirements to match supply and demand. So do I have enough supply to match my demand? And if I don't, obviously that's an S&OP process. Supply chain risk mitigation and operational feasibility on implementing inventory policies by simulating target inventory policy recommendations. A mouthful of words, but what it really means is if I start to play with the inventory policy, what's the outcome? If I want to mitigate the risk on a supplier by changing my inventory policies in other parts of the network, what's the outcome for my inventory? Lastly, understanding demand characteristics in order to develop a differentiated and segmented supply chain. So one of the issues, not all products behave the same. So some products, in terms of the demand, are very smooth. They're very predictable. There would be a lower forecast error. Other products are much more difficult to forecast, much higher forecast error. What do we do with those guys? Right, let's start jumping into it. Let's look at a very simple example. This is an inventory strategy to make to stock. So we can see, and I'll use the pointer, you can see that we've got a production time, transportation time, and a safety stock level. So they're our little legend. So supplier in Charleston and one in Malaysia and China. So again, 2 days to process or make the component, 8 days, 2 days, 3-day lead time out of Charleston to Austin, and out of Asia, 28 and 30 days into Houston. And then again with Austin, 5 days to manufacture, 15 in Houston, 1 day resupply into Dallas, 15-day manufacture, and 1 day into DC Dallas. Very simple supply chain, American. But if we put all our safety stock in the DC in Dallas, all finished goods, what's our safety stock cost? It's an example. There's some numbers behind there, about $6,000. But our response time in Dallas is 0. So if we get an order today, we can resupply today. So that's a make to stock strategy. What happens if we do a make to order at the parts level? So if we have the parts in Austin and in Houston, so we've got safety stock, see the little green buckets here. So what we've now got is a 1 day resupply to Dallas where it gets manufactured and another day into the Dallas DC. So we can see we've got a 17-day response time. So 15 to make, let me start at the other end. One to get the parts from the two manufacturing locations, 15 days in Dallas, and another one to the DC. So 15, 1, and 1, 17 days. Safety stock much lower because you're keeping it at a components level. Okay, that all makes good sense. What happens if we've got a hybrid or an integrated system? So there is the ability to actually, with a simple network, set up our safety stock so that we can have a service response time of 0 days, but a much lower safety stock. And in this case, what we're doing is, yes, we're keeping some stock at Dallas, at the DC at the finished goods level. We're keeping some in Houston, and obviously that's to get rid of the 28 and 30-day lead time out of China. So that's a bit of a no-brainer. And then we're keeping some at Charleston. So with this makeup, we can have with the appropriate levels of safety stock. So we need to determine that, and we're going to get into that detail soon. We can have a service level of 0 days, but $4,700 worth of safety stock. So the numbers are the numbers, but ultimately we know if we look at that conceptually, we can see that we can achieve very good service levels with lower safety stock compared to a make-to-stock environment. So that's the summary that we've just gone through. Make-to-stock and integrated optimizer both 0 days, and make-to-order is 17 days where you're waiting for each component to come through. So we can analyze the network and optimize on where and how much safety stock to hold in order to minimize the total holding costs given a particular service level. While the integrated system has a higher holding cost than the make-to-order, its response time is very quick. So within a business, the choice is fairly clear. If we extend that thinking within this example using the numbers that are behind the system, we can actually come up with a slide which really describes the amount of safety stock we need to achieve the service time, the number of days to service. So with 0 service days, with effectively a make-to-stock, we need just over about $4.5 million worth of safety stock within the network. That declines as we actually extend our service time to the end customer. There's a fairly rapid decrease here, and that's probably all through the manufacturing. And then while, if we're going to wait for parts, then we're getting down to 70 days. So a make-to-order would be 70 days. You wouldn't hold any safety stock, but I guess after 70 days, you wouldn't have any orders anyway. Okay, 2, 3, 4 slides on demand propagation. We need to understand this because if we're talking about safety stock, what's the driver of the safety stock is the underlying demand. So without a really good interpretation of the underlying demand, the best calculation of safety stock in the world is going to be fairly useless. So surprisingly, or not so surprisingly, you spend a lot of time understanding the demand profile before you calculate the safety stock. Why do we need demand propagation? If we're talking about a network, the demand is going to propagate down through the network. So we can only start with the customer transaction demand. That's the endpoint. That really determines the demand. The customer demand doesn't equal the facility demand because it depends on the connections within the network. So if we've got multiple DCs connected to multiple customer demands, then there's not necessarily that one-to-one we're looking for. What can happen is slow customer demand can actually merge to be a frequent facility demand. Slow selling items at 100 branches that are all sourced out of a Melbourne DC. If I look at the Melbourne DC demand, it actually could be nice and smooth and wonderful, and therefore easier to manage and easier to calculate a safety stock. But if I do that at the 100 branches, it's much harder to do. And I think we all know that ultimately, if we hold a safety stock at the DC, it's going to be far less than the sum of all the safety stocks held at the branches for the same item. It's just an absolute truism, and I just see it time and time again. And we need the demand and its associated variability at each side to calculate safety stock, which is what I said earlier. A quick lesson in some statistics. These are the statistics that LlamaSoft uses, that we use to calculate our demand characteristics. You'll be familiar, demand mean, the sort of standard mean calculation, standard standard deviation calculation, or the standard deviation calculation, I should say. We also include a non-zero demand mean. So just take those points that you have a sale and calculate the mean. Similarly, calculate a standard deviation removing the 0 points. And then you have an inter-demand interval mean. So basically what you do is you calculate the mean intervals between demand. So in this case, you can see the 2 and the 3. So there's an interval of 2 there, an interval of 3 there. So the inter-demand interval mean is 2.5 periods. So on average, there's 2.5 periods between a demand. Those fairly simple 5 statistical calculations can actually then determine the type of demand or demand pattern that you have, whether it's smooth, erratic, intermediate, etc. Those patterns are important when we're looking at the demand during that lead time, when we need safety stock to cover us in case of abnormal sales demand. So again, just looking at this, we can see that we've got a demand series at customer 1, demand series at customer 2. We've got our 5 calculations. And at the warehouse, we've got this propagated demand. So we're pulling that demand through to the warehouse. In this case, there's 2 customers to 1 warehouse, but obviously it could be multiple customers. It could be multiple branches. It really just depends. So as I said, slow customer demand could merge upstream, resulting in a frequent facility demand. Why do we need this demand classification? As I mentioned, we need to choose a best fitting distribution for the demand during the lead time. That's our risk period. So we need to understand that demand distribution. In this case, we use those 5 statistics. So we end up with smooth, erratic, slow, and lumpy, and a couple of other exceptions that we do. Again, very quickly, the age-old question of do we use a normal distribution? Normal distributions can be appropriate in many instances, but in a lot of businesses, they're probably not best to be used. And the issue really is, and this is one example that comes out of Lamasoft, but equally you can find many other examples. In this case, you're finding that 2/3 of their products are what would be classified as lumpy if we use those 5 statistics. In terms of smooth, the green, I can't see it, so I doubt that you can see it. There's literally less than 1% of items that will be classified as smooth. So you tend to end up with, not a normal distribution, but closer to I think a Gaussian distribution. And really that's the issue, is that you need to understand the best demand to get the right safety stock out of it. Again, we've got 5 customer demands coming through. Shenzhen, Guangzhou, Shanghai, etc., and they're coming up to a DC, and we can see the aggregate demand of the DC. But also now you've got the effect of batching. So when you're starting to get into the upstream network, batching starts to be an issue, and you need to take account of that batching. So the simplest example is you go into a store. That store is selling product every day. It's going off the shelves every day in 1s and 2s and 3s. But the resupply to the back of that store isn't daily. It might be every 2 days, 3 days. It might be weekly. Some products might be fortnightly, and some products might only be monthly. So you now got this batching component within the supply chain, the bullwhip effect that I think many of us are familiar with. And again, that will have an effect in terms of what level of safety stock you're going to have through the network. So you can see it's starting to get complicated. I think that's what I'm trying to say. Very briefly, again, this is just saying that in this case, a gamma probability density, that was the one I was trying to think of, is probably more appropriate than a normal probability. So different ways to look at these things. So I think what I'm saying is don't always assume that a normal distribution is going to fit the bill. Right, okay, we're going to spend the next 20 odd minutes or so going through some calculations around multi-echelon inventory optimization. Very different to single echelon approach. Single echelon is all about considering each node within the network separately and independently of upstream and downstream nodes. Multi-echelon really is looking at the network lead times and service levels, and they're all considered together. And we'll go through an example of looking at that. So we're simultaneously optimizing inventory targets across all the items and echelons and locations. So very different process. And as I've said in my first webinar, and I spoke last year or 2 years ago at the SMART conference, really multi-echelon is really the way in which inventory optimization is moving. The ability to look at the network and the ability to look at inventory flows rather than static inventory levels. And I think that's really the next wave that we're going to have within this industry is looking at inventory flows and optimizing inventory flows through an entire network, not isolated nodes within that network. Sorry, just taking a drink of water. So key concepts, some things we've got to need to get our head around. So hopefully you've finished your sandwiches and you're refreshed. And I'd really urge you for the next 10 or 15 minutes to pay attention. I'm also addressing that to myself. we need to think hard and concentrate on these concepts as we go through. So it'll be worth it when, as I say, you might have that aha moment when it all sort of fits together. So a multi-echelon network structure, suppliers, manufacturers, DCs. Fairly straightforward. You could add branches, you could add regional DCs, you can add multiple suppliers, a supplier that goes through a supplier. The system is composed of stages, nodes, sites. A stage represents a major processing function. Stages are grouped into echelons. So we've got a supply echelon, manufacturing echelon, DC echelon. Stages to the left are upstream, those to the right are downstream. So that's typically the way we do it. If I mention it the other way, please forgive me, I've lost track of what I'm saying. Interesting enough, speaking to someone the other day who was saying they were speaking to an auto manufacturer in the US. You can probably have a good guess. There are only 2 or 3 that are common. And they had done the analysis and they had 60 echelons within their supply chain. So there were effectively 60 levels of manufacturing, of storage, of value adding through their entire supply chain. So it can get quite complex quite quickly. So interesting. Safety stock optimization. 2 key concepts we're going to talk about, and we need to understand these. Service time. Service time is the period of time between order, receipt, and order dispatch. So it's expressed in days. So how many days between receiving the order and dispatching the order? Coverage is the net risk period that a site safety stock will cover. So coverage is, again, in days. So, for instance, you might have 7 days worth of cover. So that means that I've got 7 days in which I can cover the safety stock. SSO optimizes service times to minimize total safety stockholding costs across the supply chain. So that's really the issue, is we're going to optimize the service times, and then we use coverage and lead time demand distribution to optimize the safety stock levels. So we'll get into a simple example which will start to make sense. So first couple of slides. Again, we're going to use this as an example. Manufacturing with a production time of 2 days. Transport time between manufacturing and DC is 7 days. And internally, there's a review period. There's a 1-day review period. So our immediate lead time, which is the lead time from the nearest upstream node. So for the DC, so for this DC, its immediate lead time is the review period of 1 day, plus the 7 days. So that's 8 days. The immediate lead time for manufacturing is, again, it is the 2 days production time plus the 1 day review time, review period. So that's 3 days. So immediately we can see that the entire lead time for that little supply chain is 11 days. So the maximum lead time from the farthest upstream node, so from this perspective, it's manufacturing, is the immediate lead times of the manufacturing and the DC, so the 8 plus 3 is 11 days. So that's fairly intuitive and fairly straightforward. But we need to understand that as we go into the next stage. Service time is a period of time between order receipt and order dispatch. I've mentioned that. Coverage is the net period of risk that a site's safety stock will cover. So if a transport time is 6 days into a DC, and now we've got a customer, and what we assume is the service time at a customer-facing site is always 0 days. So from we always assume that, and we're going to assume that in the network model, but it doesn't have to be. But what that really means is a service time of 0 means that a customer gives me an order, I dispatch it the same day. So there's 0 wait time. So orders need to be shipped out immediately upon receipt. In this case, the DC would need to hold safety stock to cover a 6-day risk period. So our transport is 6 days. So if I get an order today, I don't have stock, I've got to wait 6 days. Therefore, I need 6 days of stock or 6 days of coverage at my DC to maintain a service level of a service time of 0 to my customer. So coverage of 6 days for a service time of 0. Now, what if I say the service time of the DC is 2 days? So we break our assumption of 0, so we make it 2 days. So the customer has to wait 2 days. So the DC promises customers to ship out orders within 2 days. So the net period of risk, or the coverage, is now my 6 days, which is my transport lead time, my ILT, minus my 2 days, my service time, leaves me with 4 days. So at my DC, I would have 4 days of coverage. So that would, at worst case scenario, mean I could meet a 2-day service time to my customer. What if service time of DC is 6 days? So if I said I have a service time of 6 days of the DC, so the customer's got to wait 6 days, well, there's no safety stock. It's effectively a make to order because I've got no stock in my DC, so every order has to wait 6 days. So that's how the system is working. Right, so we're going to get into the next one. So let's add some manufacturing back here. So we've got a production time is 5 days. Our transport time is still 6 days. So we're building up our example. Okay, the service time for a non-customer facing site, because what we assume customer facing site service time is 0. So the service time for a non-customer facing site is an optimization decision variable. So we can determine that. So effectively we're determining the service time through our network. If service time quoted by manufacturing is 0 to the DC, then they must have a coverage of 5 days. They must have 5 days worth of stock at manufacturing in order to ensure that they can always supply the DC with same-day deliveries. So the DC coverage would be 6 days. So that is equivalent to an echelon safety stock optimization. So if I have 5 days of safety stock here, 6 days of safety stock here, that's a single echelon because I've treated each echelon independently of each other. If the service time quoted by manufacturing is 3 days, so 5 production days minus the 3 service days, means my coverage is 2 days. So there would be 2 days worth of stock at manufacturing because that's what they would be promising. My coverage at my DC now is obviously, is obviously the 6 days that we need to cover the DC plus the 3 days that potentially we're getting out of manufacturing because they're giving us a service days of 3. So suddenly, we're waiting our coverage of the DC is 9 days. So in order to optimize the total safety stock cost, what is the service time of MFG? And that's a multi-echelon inventory optimization question. So we're going to start to get into exactly that calculation now. So our coverage, you can start to see the calculation. So our coverage, so this is effectively our safety stock days at points in the network, is calculated as our immediate lead time. So we're looking at the coverage at this point. So it's our immediate lead time. So it's the lead time from there to there, plus my service days at my supply point, less the service days this point is offering to the next customer. So immediate lead time plus service time from the previous node, previous echelon, less the service time from the current echelon. And we'll get into some examples and we'll see that flow. So, right, I think this is the last bit of knowledge we need. So manufacturing with a 1 day production, service time of 1 day, 3 day lead time, DC1, service time of 2 days, 2 day lead time, DC2, service time of 0 because that's the customer. So that's always our assumption with a 2 day lead time to the customer. So the total coverage across all stocking sites equals the maximum lead time at the customer facing echelon. So we can go through the coverage at each of these levels. And if we add that all together to give us our total coverage, we're going to come to our 6 days. And that is our total time. 1 day to manufacture, 3 to deliver to DC1, plus another 2 to deliver to DC2. So that gives us our 6 days of coverage to DC2. Right, so we're just going to look at a couple more slides and we'll get into the example. So one of the key concepts is a safety stock curve. So you saw in that previous example, just popping back, we had a maximum coverage of 6 days to DC2. So our safety stock here and our coverage, so this will go up to a maximum lead time, which in this case will be 6, is as we look at our coverage across that network between 1 and 6 days, we can't go past 6 days, it's pointless anyway, you can actually see that we have a flattening of the curve. And this is the risk pooling effect. So as you start to pool the risk into that downstream, typically that downstream echelon, you're starting to aggregate all those demands, which start to net off, which gives you a risk pooling, give you effectively lower safety stock. So, so a coverage for a stocking point may range from 0 to the maximum lead time of that stocking point. So there's no point having more stock, more coverage at a point than the lead time from to that stocking point. So that provides an upper bound on your coverage. You don't need more. The flattening of the curve is the result of the risk pooling effect. And what that means is really that, as I said, the variability is reduced if one aggregates demand across multiple DCs. And it gets back to that whole issue. If I keep all my stock in the DC, I'm going to have lower safety stock than I'm keeping it all at the branches. So this is a graphical mathematical representation of something that we know. So in this case, if we look at our same example, we're just using a normal distribution for our demand. We've got some numbers in there, service requirements 95, et cetera, and these are the numbers that would come out of this simple example. So, 0 day coverage, so that's a make to order, no safety stock, 245, 6 days. That's going to probably be a make to stock environment. And you can see this flattening out. So each day of coverage, we can actually work out the amount of safety stock we need in the network. So what does that sort of look like when we apply it to our little example? So if we've got 1 day of coverage at manufacturing, then there's 100 units of stock that we would need there. If we move the coverage up to our DC1, so we would have 4, so 1 plus 3, we would have 4 days cover at DC1. We go up the curve to 4 days, we would be 200 units. And then if we have 6 days at DC2, so our 1 day, 3 days, 2 days, so all our coverage at DC2, we would have 245 units. So depending on where we put the coverage through our supply chain, we'll have different effects. And we'll see the cost implication of that in our final example. So what is the least cost set of values for service time? Well, in a single branch network, the decisions are straightforward. The safety stock curve always makes it cheaper to hold the safety stock pooled, and some is required at the DC to maintain the service level. So it's always best to keep it at at the final point. In a network with lots of consolidations and lots of distribution branches, decisions become more involved. So in a more complicated network where you've got choices of flow, how do you what's the best choice? And again, that's all coming down to our MEIO optimization. So for instance, if we, in our example, if we allocate $5 per unit holding cost at manufacturing, $10 per unit at DC1, and 12, so mimicking a normal supply chain where you're adding value. A single echelon really puts it independently across each site. In this case, we're using a multi-echelon baseline. So we're going to say we're going to have 3 days here and 3 days there, okay, for want of a better example. And then we're going to look at a multi-echelon optimum. So what do we see? So single echelon, we have 1 day here, 3 days here, 2 days here. So we're covering the lead time into that echelon with stock. We can do the calculation. There's our 6 days total throughout our network. We end up with $4,000. Our baseline, we're just going to say 3 days at DC1, 3 days at DC2. And that's fine. That doesn't break the maximum, because we can see there's 3 days lead time into DC1, so we can hold 3 days there, and 3 days for DC2, so we're holding an extra day at DC2. 6 days, what's the total? 3,800, because obviously we're holding less units, but more costly units. Our multi-echelon, what does it come up with? It comes up and it says actually the best outcome is to hold all 6 days at DC2. So 245 units, even at a slightly higher unit cost compared to DC1, that gives us the best result. But what happens if we start to change the costs? So, I've jumped ahead 1 slide too many. This actually just shows you what I've just said. The pooling effect will reduce the total safety stock if the safety stock is consolidated at fewer sites. And we can see that, and that's the baseline and the optimal. But what I was jumping ahead to say, what happens if we're holding $30 per unit at DC2? Then it starts to change. We saw that our previous optimal was holding it all at DC2, 6 days. What we now find is the cost of holding stock at DC2 is much higher. So what it does, it tends to push the stock downstream, or to the upper echelon sites, I should say. So we've moved 4 days to DC1 and only keeping 2 days at DC2. Now, 2 days is the minimum we need to hold at DC2 in order to have a 0 service time to our customers. So we can't go below 2, so that's locked in, but we can move up to 4 days back to DC1, and that's what we're doing. So 4 days is 200 units, 2 days is 144 units. And all these units, didn't quite explain that. Let's just go back. These 1 day, 100 units, 3 days, 173 units. It's all coming from that graph that we saw, earlier. 1 day, 100 units, 3 days, 173 units. So we're picking up those units from that graph, from the profile that we've calculated from our demand, our underlying demand profile. So we can see very simply how increasing the holding cost of DC2 will push the safety stock to those upper echelon sites. So that's what starts to happen as we start to play with the costs of holding. The optimal inventory flow through our network will change. It will ebb and flow with the tide. It will change according to the variables that we have. And you can imagine, as we go through each month end, the demand profile may change, our cost may change. What can happen, and I'll just digress for a few moments, what can happen is you can potentially end up with a system that becomes unstable. So if I'm looking at changing my inventory flows every day according to the latest currency rates, et cetera, you end up with an unstable system because your inventory flows will start to change, and typically they'll step change. There'll be an important variable that will tip the flow from one direction to another direction. So typically we wouldn't suggest that you do that. What we would suggest is that once you've set up your network flow, you would keep it in that state until one of those important variables change significantly. So if the US Aussie dollar rate changed significantly, that might implicate that different supply routes be chosen. We can't open and close DCs willy-nilly. So, we can't suddenly go from 2 DCs to 1 DC. So there's constraints within the system that you have to use. But again, there will be variables that the network is sensitive to that over time may point to the fact that, guys, we may need to go from 2 DCs to 1 DC because the second DC is just costing us too much. So when you look at these solutions, when you look at these multi-echelon inventory optimization solutions, when you look at your inventory flows, there's a level of stability that has to be respected within that. We're not going to tinker every day according to the latest set of values. We're really only going to remodify our inventory flows when significant variables change. So in terms of just a couple of summary slides, the multi-echelon safety stock optimization formulation, it's the lead time demand distribution. So each of these, we need to understand during our lead time, what is our demand distribution looking like? Is it going to be more like a gamma, or is it going to be more normal, plus all those other strange ones that we can get? We can propagate that demand, downstream in our network. There's, from demand propagation and demand analysis. The safety stock curve. So this is a safety stock curve. So we're generating a safety stock curve between the coverage and the safety stock at each point, respecting the maximum coverage that you have for that particular point in the network. As you go through the network, you can aggregate that coverage because you can take the lead time from the uppermost point, and you can increase your coverage. So in a sense, we can have all our coverage sitting at our DC, our last point, which then takes the entire lead time, and we saw that in that very first example that we showed. Or we can spread that safety stock through our network, which will potentially give us the same service days outcome to our customer, but a lower overall value, as we saw in the example we just went through now. You formulate the problem using the safety stock curve and constraints and solve for coverage and service time for each site. So we have this process where we use a solver, which a smart piece of software goes through all of those different inventory flows and is then able to, even in a 60 echelon problem, figure out where you should hold the safety stock based on the coverage for that echelon, and based on the service time that echelon needs to provide. So recap, and I hope you're all still there. Recap is each stage quotes a guaranteed service time to its downstream stage. So that's an important issue, and we talked about that. The safety stock optimization is the service time between echelons is the decision variable, whether we provide a service time of 0 up to the lead time at that point. The model will consider all service time combinations. Even in our simple example, there was there were several combinations we could have. We could have 6 days at the end. We could have 2 days at the end plus 4 days, or etc. It obviously gets very complex, more complex in the real world. But those service time combinations determine a configuration that satisfies service level requirements. So that is our constraint. That's our objective, I should say, is that service level requirement with the least inventory cost. And so the goal is to optimize those service time to minimize the inventory costs. Now, well done. You've stayed with me. It is complex. The concepts are really fairly straightforward. There is some complexity there. I hope that the examples I gave today were fairly straightforward. There's enough there to be able to think about it. I'm almost certain that this will go onto the website, so you can go through this at your own pace and perhaps understand it better than I've tried to explain it. And as Clint said earlier, if you are doing that and you've got some questions and something it doesn't understand, send it to Clint. Clint will pass on to me, and I do promise to respond to every request that I do receive. I just want to end by saying thank you. Thank you for your time. Find us, me, at the SMART Conference, March 29 to 30 at Darling Harbour. If you're in Sydney or you can get to Sydney during that period, I'd encourage you to come to the premier conference that's been held in Australia. It is a great conference. If you can't make the conference, make the expo. We are the coffee sponsor, so the coffee will definitely be on me. And if you come and you find me and you say that you listen to this webinar, as a reward for staying the distance, you will get a free coffee cup. So that's my gift to you today for lasting the distance. So I'm going to sign off and hand you back over to Clint.
Thank you, Sean, and thank you all for attending this afternoon. I hope you got quite a bit out of it. I know my mind is still bouncing around trying to work all that out, but then again, I don't work in supply chain, so hopefully you guys who do work in supply chain, that all made quite a bit of sense, and you've been able to learn a little bit more about all that is MEIO. Guys, like Sean has mentioned, he is not only at the SMART Conference, but we are definitely at the SMART Conference. So please come via our booth, which is C21, I believe. And we'll actually be running live podcasts throughout the 2-day conference. So come along and watch us do our thing on the ASCII Lounge. And hopefully you'll get to hear some really good insights from various different thought leaders that we have lined up for the 2-day conference. As always, if you do have any questions, comments, concerns, or we can help you in any way, please feel free to email us at events@ASCII, that's asci.org.au. Our old emails do still work, so we will be checking those, but always good to start getting the new out there. And please make sure you keep an eye out on our events board for new webinars coming up. We're always running these quite regularly. All right, we, as I'm just being reminded by Sean as well, there is also going to be part 3, thank you, Sean, of the Multi-Echelon Inventory Optimisation, or MEIO for short, so make sure you keep an eye out for that one. Guys, thank you very much for your time this afternoon. Enjoy the rest of your day. Catch you later.